Hi, Core Chemistry, Mrs. KJ here, going over Lesson 5.05, Types of Reactions, Part 2. All right, so in the last lesson we talked about combustion, synthesis, and decomposition reactions. This time we are going to talk about single displacement, which is when one element is displaced or they switch places. We have a double displacement where two elements are displaced or switch places. They're also sometimes called replacements instead of displacement. So single displacement is the same as single replacement. Double displacement, same thing as double replacement. It all depends on what textbook you're learning from. Chemical reactions, remember, happen because elements gain, lose, or share electrons. So if specifically we're talking only about gaining and losing, when electrons are gained, it's a reduction reaction. And when electrons are lost, it's an oxidation reaction. So we're talking about some more specifics here regarding gaining and losing electrons. In this lesson, you will learn about three types of chemical reactions: oxidation-reduction reactions, single displacement reactions, and double displacement reactions. You will see that some of these reactions can be placed in more than one category. Goals for the lesson: recognize the different types of chemical reactions, define single displacement reactions, define double displacement reactions, describe oxidation, describe reduction, identify reactions that involve oxidation and reduction, explain what happens in oxidation and reduction reactions, compare and contrast the products and reactants of single displacement reactions, compare and contrast the products and reactants of double displacement reactions. As always, you can log in and get the student guide, but either way, make sure you are taking notes. Types of reactions include single displacement, double displacement, and oxidation-reduction reactions. You will study 6 types of chemical reactions in this course. This lesson examines 3 of these: single displacement, double displacement, and oxidation-reduction reactions. As you learn about these reactions, you will look at examples that may be relevant in your life. Keep in mind that some categories of reactions can overlap. For example, a single displacement reaction can also very easily be an oxidation-reduction reaction. The diagram is showing. So single displacements can be their own thing, but they can also be included sometimes in an oxidation reduction, and sometimes oxidation reductions are not single displacement reactions. Chemical reactions, elements are replaced by other elements. This lesson will look at a type of chemical reaction called a single displacement reaction. The general equation for a single displacement reaction is the following. So you have a compound, AX, showing the 2 different elements, plus B, another element, yields A plus BX. So if you notice, the X was attached to the A, and now the X is attached to the B. So it's switched partners. All right, so add down the definition. So hit pause as you need to add to your notes. And here it simply shows us that X switches partners. Now something you might have noticed with this is where the X is. So it's AX, and then notice how it's BX. It's not XB. That's very important. That has to do with, can you think of why? It has to do with positives and negatives. So for AX, the A, is it the cation or the anion? It's going to be the cation because you always write the positive one first. So that tells us that X is an anion, which tells us that B has to be a what? A cation if X is going to attach to it, because only positive and negative will combine. So it has to be written BX. In a single displacement reaction, the reactants are always one element and one compound. Notice that when the reaction occurs, the element X in this generalization equation switches partners. When it is a reactant, it is paired with element A. When it is a product, it is paired with element B. This is a pattern that you can use to identify this type of reaction. In this reaction, X is an anion, the negatively charged part of a compound. Since the cation part of the compound changes from A to B during the reaction, this type of single displacement reaction is called a cation displacement reaction. Anion displacement, single displacement reactions also occur. In other words, had B been an anion, then which one would have had to have partnered with it? If B was an anion, then the A would have had to go with it. So it would be AX plus AB in that case. Single displacement reactions are also known as single replacement reactions because one element is replaced by another. Metals can replace metals in a single displacement reaction. Suppose you were to drop a sample of magnesium metal into a solution of copper sulfate. What would happen? Over time, the magnesium would replace the copper in the solution. This would form magnesium sulfate. Copper metal would also form. The metal in the reactant compound copper is replaced by the metal magnesium. This is a single displacement reaction. So here we have the before. A strip of magnesium metal is added to the copper sulfate solution. So right now the metal is magnesium, but they actually switch place. And the copper comes out of this blue. It really is that pretty blue in real life. It comes out of the blue, and the copper is going to accumulate. So it's pretty crazy. Notice again how the metals switch places in a single displacement reaction. So if we have iron plus copper sulfate, now we have iron sulfate plus copper. Suppose you place an iron nail in a solution of copper sulfate. The reactants will undergo a single displacement reaction. The copper will switch places with the iron and slowly accumulate on the nail. The reaction looks like this. Iron plus copper sulfate yields iron sulfate plus copper. Suppose you were to perform this reaction the other way. What if you put copper into a solution of iron sulfate? Would you end up with an elemental iron and copper sulfate? Now, on first thought, you might think, okay, positive and negative, yep, they can switch places. In this case, which you weren't expected to know ahead of time, it is no, not all are reversible. So sometimes they can reverse and go backwards, but not always. This is a case of when they can't. Information about iron sulfate. Iron 2 sulfate is called ferrous sulfate. Iron 3 sulfate is called ferric sulfate. Both are used in water treatment plants. They are added to the sewage or polluted water and have a tendency to settle to the bottom of the tank, carrying the pollutants with them. That's kind of interesting. So again, ferrous and ferric, I forget if it's Greek or Latin, but that's why iron is abbreviated Fe. So again, some of these elements that were used in everyday life before chemistry really got started as a solid science. The 2 and the 3, what does that tell us again? That tells us that the iron has a +2 charge in this case, and in this example, the iron had a +3 charge. The activity of an element will determine whether or not it's replaced. So here I said you're not expected to know if the iron and copper would trade places if you start out with this as your reactants. However, there is a table that tells you. In the previous example, iron replaced copper in a single replacement reaction, but copper will not replace iron in the reverse reaction. That is because copper is less reactive than iron. The reactivity chart here on the screen is called the reactivity series. A more reactive element will replace a less reactive element, but not the other way around. So here we have iron. Down here we have copper. So iron is more active. It's got more energy. It wants that combination of the stability more. It will kick that copper out of the way. But copper cannot kick the iron out of the way. In this list, iron is more reactive than copper, and thus the reaction goes in this direction, we say. In other words, the iron will replace the copper. It proceeds much more strongly from left to right than right to left. In other words, we would not have the arrow pointing to the left because the copper is not going to kick out the iron. All right, let's go to the next one. In a double displacement reaction, 2 compounds exchange ions to form 2 new compounds. Let's say you go on a double date with your best friend. Partway through the night, you realize that you like your friend's date better than yours. The thing is, your friend likes your date better too. So you switch partners and everyone is happy, and it sounds like a really sad comedy show. This is the basis of a double displacement reaction. Double date or double displacement. Ha 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 ha. Double displacement reactions follow the following pattern. AX plus BY yields AY plus BX. Obviously, you can use any letters you want. They use the X and the Y because they're at the end of the alphabet to help you remember to keep them at the end of the compound. So A was with X, now A was with Y. BY becomes BX. Why do the A and the B's have to be written first? Because they are both the cation, and you have to write the positive ion first. This equation shows how two compounds as reactants form two different compounds as products. The two ions, X and Y, switch partners. A double displacement reaction is also called a double replacement reaction. Chemists use both terms. So, bada boom, bada bing, they change partners. Some double displacement reactions will result in a precipitate. All right, we talked about one of these in the previous lab. A yellow lead iodide precipitate forms as soon as lead nitrate is dropped in potassium iodide. All right, so write down precipitate if you don't know that word already. Precipitate equals when two liquids chemically react and form a solid. It's not freezing. It's a chemical reaction where something new is created and that new thing is a solid. Some double displacement reactions are sometimes called precipitation reactions because one product is often insoluble, cannot dissolve, so it's an insoluble solid that separates from the solution. In some double displacement reactions, one of the products may be only slightly soluble. This product will become a precipitate and drop out of the aqueous solution. So slightly soluble means it might take a little more time or you might not see as much of it. Aqueous, meaning that it was dissolved in water. For example, 2K, I'm pretty sure this is supposed to be an I. I've never seen an I written like that. All right, yes it is an I. All right, so 2 potassium iodides plus lead 2 nitrate yields lead iodide, which is a solid. That's what that S stands for, plus 2 potassium nitrates. So the solid compound lead iodide is insoluble in water and therefore is our precipitate, which we show by putting an S in parentheses. If something's a liquid, we could put it with an L in parentheses. If something's a gas, we put what in parentheses? A G. And sometimes with aqueous, we show it's dissolved in water by putting AQ in parentheses. Many reactions involving oxygen are called an oxidation reduction. All right, so now we're getting to our last type that we're going over today. You probably think of the formation of rust when you hear the term oxidation or oxidate. That is correct, but in this lesson you will take your understanding of oxidation to the next level. Let's take the equation 2 magnesium atoms, oh they're solid, equal, this should be a plus side, so 2 magnesium atoms plus dioxide as a gas yields 2 MgO as a solid. And what's wrong with this G? It should be lowercase. Ooh, whoever wrote this for K-12 was having a rough day. Yes, here we go. Here, it's written decently over here. Let's look at this one over here. Yes, it is a combustion reaction and a synthesis reaction. Okay, why is it a synthesis? Because we have two things that are creating one. It's a combustion. How do we know? Well, we see it's reacting with oxygen, and what else should be a product to show us? Energy. And so obviously we're going to have some kind of combustion, explosion, or fire. But it's also a kind of reaction called an oxidation reduction reaction. The magnesium in the equation gained oxygen. In other words, it has been oxidized. All right, so an oxidation reduction reaction equals, make sure it's in your notes, a type of chemical reaction that involves the exchange of electrons between reactants, often defined as the addition of oxygen to and removal of oxygen from the reactants. Okay, so really there's two different definitions. We can talk about it in terms of oxygen being added or taken away. The more correct definition is we talk about which one of the reactants is gaining electrons and which one's going to lose electrons. So the magnesium gained oxygen, so the oxygen attached to it, so we say the magnesium was oxidized. If the reaction is reversed, so if we turn it into a decomposition reaction, the magnesium loses the oxygen, they separate out, and we would say that the magnesium is reduced. So less oxygen, it's reduced to its simpler elemental form. This reaction is an oxidation reaction going to the right, but if it goes the other direction, to the left, and becomes a decomposition reaction, then it would also be a reduction reaction. So it all depends on which way the arrow is going, if it's an oxidation or a reduction. Some more about this in part 2.